Message properties in AMQP091. In the context of AMQP091, every delivery consists of message metadata and delivery information. Different client libraries may provide access to these properties in slightly different ways. Typically, delivery handlers have access to a delivery data structure that allows them to interact with these properties. Delivery and routing details as properties. It is important to understand that some properties in AMQP091 represent delivery and routing details rather than being considered message properties themselves. These properties are automatically set by RabbitMQ during the routing and delivery process. Description of specific properties. Delivery tag. This property is a positive integer that serves as a unique identifier for the delivery. It is particularly relevant in the context of publisher confirms. Redelivered. This property is a Boolean value that indicates whether the message has been previously delivered and requeued. Exchange. The exchange property specifies the name of the exchange that routed the message to its intended destination. Routing key. This property represents the routing key used by the publisher when initially publishing the message. It provides information on how the message should be routed within the messaging system. Consumer tag. This property is a string identifier associated with the consumer or subscription that received the message. This code demonstrates how to connect to a RabbitMQ server, declare a queue, and publish a message with properties using the Pika library. Let's break down the code. To publish a message to the queue, channel.basic_publish is used. The message is published to the my_q queue with the body hello RabbitMQ. Additionally, message properties are set using the properties parameter. In this example, the message is set to be persistent, delivery_mode equals 2, meaning it will survive a broker restart. The content type is set to text/plain, and custom headers are added. The correlation_ID property can be used to correlate related messages. This code snippet demonstrates how to consume messages with properties from a RabbitMQ queue using the Pika library. Let's break down the code. The code defines a callback function named callback. This function will be invoked when a message is consumed from the queue. It takes 4 parameters: ch, the channel, method, delivery details, properties, message properties, and body, the message body. Inside the callback function, the code prints the received message using print received message body. You can modify this part to perform any desired processing or handling of the message. The code then prints various message properties for informational purposes. It retrieves the delivery tag, whether the message is redelivered, the exchange used to route the message, the routing key, the consumer tag, subscription identifier, the content type, the headers, and the correlation ID. Next, the code uses channel.basic_consume to start consuming messages from the queue named my_queue. It takes the queue parameter as the name of the queue to consume from and the on_message_callback parameter as the callback function to invoke when a message is received. The auto_ack equals true parameter enables automatic acknowledgement of messages. This means that RabbitMQ will consider messages as acknowledged as soon as they are delivered to the consumer. You can modify this behavior based on your application's requirements. Finally, the code calls channel.start_consuming to start the consumption process. This function sets up the necessary communication channels with RabbitMQ and begins receiving messages. Message properties. These are message properties to be set at the time of publishing. Most of these are optional. Delivery mode. This property indicates the delivery mode of the message. It is an enum with values 1 or 2. The value 2 represents persistent mode, meaning the message will be stored in a durable queue and survive broker restarts. The value 1 represents transient mode, where the message will be stored in memory and may be lost in case of a broker restart. A real-world example of using the delivery mode property is storing order information in a durable queue to ensure that orders are not lost even if the broker goes down. Type. The type property is used to specify an application-specific message type. It can be any string that identifies the purpose or nature of the message. For example, in an e-commerce system, you might use user.registration as the type for messages related to user registration, or payment.process for messages related to payment processing. This property helps consumers understand the meaning or context of the message. Headers. Headers are an arbitrary map of key-value pairs associated with the message. They provide additional metadata or custom information about the message. You can include any string header names and corresponding values. For example, priority, high version 1.2.0 could be used to specify the priority level and version of the message. Headers can be used to convey application-specific or contextual information that consumers can utilize for processing or routing decisions. Content type. The content type property specifies the type of data contained in the message. It typically follows the MIME, multipurpose internet mail extensions, standard, and can be values like applications/JSON or text/plain. This property helps consumers understand how to interpret the message payload correctly. For example, if the content type is set to applications/JSON, it indicates that the message body contains JSON formatted data. Similarly, text/plain implies plain text content. The choice of content type depends on the specific data format or structure used by the application. Content encoding. Content encoding refers to the compression or encoding applied to the message body. Common encoding methods include gzip, deflate, or identity, no encoding. Content encoding is typically used to reduce message size or improve transmission efficiency. For example, if the message payload is compressed using gzip, the content encoding property would be set to gzip. Consumers can then decode the message body using the specified encoding method to retrieve the original content. Message ID. The message ID is an arbitrary identifier assigned to each message. It can be useful for tracking or referencing messages within a system. For instance, you could use a unique identifier like ABC123 or Message 456 as the message ID. Consumers can use the message ID for message deduplication, tracking message flows, or implementing request-response patterns. Correlation ID. The correlation ID is a value that helps correlate requests with responses in a distributed system. It is typically used when a client sends a request message and expects a corresponding response. The correlation ID allows the response message to be associated with its corresponding request. For example, request 123 or response 789 can be used as correlation IDs to establish the relationship between request and response messages. Reply to. The reply to property carries the name of the response queue. When a message requires a response, the reply to property specifies the queue to which the response should be sent. This property enables the requester to provide the necessary information for the responder to send the response back to the correct destination. For example, user.service.response or email.reply can be used as the reply to queue name. Expiration. Expiration specifies the time to live, TTL, for a message. It determines how long a message remains valid or available for consumption after being published. The expiration property is typically set as a time duration in milliseconds or as a specific timestamp. Messages that exceed their expiration time are considered expired and may be discarded or deadlettered by the broker. For example, setting the expiration to 5,000 means the message is valid for 5 seconds before it expires. Timestamp. The timestamp property represents an application-provided timestamp associated with the message. It can be used to indicate the creation or modification time of the message. The timestamp value can be a Unix timestamp, an integer representing the number of seconds since January 1, 1970, or a formatted timestamp string such as May 1, 2022, 10:30. Inch. This property helps in tracking and ordering messages based on their creation or modification times. User ID. The user ID property represents the user ID associated with the message. It is typically used in systems that require message authentication or authorization. The user ID can be validated to ensure that the sender of the message is a trusted entity. For example, user123 or admin456 can be used as user IDs associated with specific messages. App ID. The app ID property denotes the name of the application that published the message. It helps identify the source or origin of the message within a multi-application or multi-service environment. For instance, order service or payment gateway can be used as the app ID to indicate which application produced the message. Ensuring data safety. In messaging applications, ensuring data safety is a collective responsibility shared by applications, client libraries, and RabbitMQ cluster nodes. This section focuses on various aspects related to data safety. Network failures and message delivery. Network failures can occur in unpredictable ways, and detecting such failures may require time. Consequently, when a client writes a protocol frame or a set of frames, example, a published message, to its socket, it cannot assume that the message has reached the server and was successfully processed. It is possible that the message could be lost during transmission or experience significant delivery delays. Publisher-side confirmation mechanism. To address these challenges, a publisher-side confirmation mechanism was developed. This mechanism parallels the consumer acknowledgements mechanism already present in the messaging protocol. It allows publishers to track which messages have been successfully accepted by RabbitMQ, ensuring greater reliability and data safety. Strategies for using Publisher Confirms. Publisher Confirms provide application developers with the means to monitor the acceptance of messages by RabbitMQ. There are several commonly used strategies for utilizing Publisher Confirms. Individual message publishing with streaming confirms. Messages are published individually. Asynchronous API elements such as confirm event handlers, futures/promises, etc., are employed to handle confirmations. This strategy offers good throughput and ease of use. Publishing a batch of messages and waiting for confirms. Messages are published in a batch. The publisher waits for all outstanding confirms before proceeding. This strategy balances throughput considerations and confirmation handling. Individual message publishing with confirmation before proceeding. Messages are published individually. The publisher waits for each message to be confirmed before proceeding with publishing subsequent messages. This strategy significantly impacts publisher throughput and is generally discouraged. These strategies differ in terms of their impact on throughput and ease of use. Application developers can choose the strategy that best aligns with their specific requirements and constraints. Please remember to implement appropriate data safety measures in your messaging applications to ensure reliable message delivery. The diagram illustrates the flow of data from the application to the RabbitMQ cluster, along with the inclusion of publisher acknowledgements to ensure data safety and reliability in the messaging system. Publisher acknowledgements represents the mechanism of publisher acknowledgements. It is a feature provided by RabbitMQ and implemented in the client library. Publisher acknowledgements mimic the consumer acknowledgements mechanism already present in the protocol. They ensure that the publisher receives acknowledgements from the RabbitMQ cluster regarding the successful processing or delivery of the messages sent by the application. Scenario: Order processing system. In an e-commerce application, let's consider an order processing system that utilizes RabbitMQ for handling incoming orders. The system receives orders from various sources and needs to ensure the reliable processing of these orders while maintaining data safety. In this example, publisher confirms are utilized to ensure that each order is successfully accepted by RabbitMQ before proceeding with the next order. It enhances data safety by providing reliable delivery guarantees and reducing the risk of message loss. Publisher confirms are enabled on the channel using channel.confirm_delivery. A queue named order_queue is declared for order processing. The publish_order function is responsible for publishing orders to the order_queue with the delivery mode set to 2, persistent. The handle_confirmations function is invoked when a confirmation is received from RabbitMQ. It differentiates between acknowledgements basic, ACK, and negative acknowledgements basic, NACK. The handle_confirmations function is registered as the callback to handle confirmations using channel.add_on_return_callback. Orders are published using the publish_order function, and the system waits for the publisher confirms. The result of each message publishing is checked, and the appropriate message is printed to indicate success or failure. Streaming confirms. In most client libraries, including the RabbitMQ Python client, Pika, developers have the ability to handle individual confirmations as they are received from the server. These confirmations arrive asynchronously, aligning with the inherent asynchronous nature of publishing in AMQP 091. This approach enables safe publishing with minimal overhead. Algorithm for streaming confirms. The typical algorithm for utilizing streaming confirms involves the following steps. Enable publisher confirms on a channel. For every published message, create a map entry that links the current sequence number to the corresponding message. Upon receiving a positive acknowledgement, ACK, remove the corresponding map entry, indicating the successful acceptance of the message. In the case of a negative acknowledgement, NACK, remove the map entry and take appropriate actions, such as scheduling the message for republishing or implementing alternative handling mechanisms. Python. In this Python example, the Pika library is used to handle streaming confirms with RabbitMQ. Before jumping into the main flow, let us first focus on this function handle_confirmations. Once we understand this function, we will be in the position to understand the main flow better. The main flow will be explained in the next screen. This code snippet demonstrates how to handle acknowledgements and negative acknowledgements received from RabbitMQ. It allows you to keep track of the processing status of each message and take appropriate actions based on the acknowledgement type. The handle_confirmations function handles acknowledgements, basic, ACK, and negative acknowledgements, basic, NACK, received from RabbitMQ. The handle_confirmations function takes a frame parameter, which represents the frame received from RabbitMQ. Inside the function, it checks the frame.method.name to determine whether it's an ACK or NACK. If the frame.method.name is basic, ACK, it means a positive acknowledgement, ACK, was received. This indicates that the message was successfully processed by RabbitMQ. The delivery tag is extracted from frame.method.delivery_tag. The delivery tag uniquely identifies the message that was acknowledged. It checks if the delivery tag exists in the message_map dictionary using if delivery_tag in message_map. If the delivery tag exists in the message_map, it means that the corresponding message is still present and has not been removed yet. The message associated with the delivery tag is removed from the message_map using del message_map, delivery_tag. The function then prints a message indicating that the message with the delivery tag was confirmed and processed successfully. If the frame.method.name is basic, NACK, it means a negative acknowledgement, NACK, was received. This indicates that there was a failure in processing the message by RabbitMQ. Similar to the ACK case, the delivery tag is extracted from frame.method.delivery_tag. It checks if the delivery tag exists in the message_map dictionary using if delivery_tag in message_map. If the delivery tag exists in the message_map, it means that the corresponding message is still present and has not been removed yet. The message associated with the delivery tag is removed from the message_map using del message_map, delivery_tag. The function then prints a message indicating that the message with the delivery tag failed to be processed. Now let us understand the main code flow of streaming confirmations. This code demonstrates a pattern for enabling publisher confirms, publishing messages, and handling message confirmations using callbacks in Python with the Pika library. The provided code defines a function named handle_streaming_confirms that is responsible for enabling publisher confirms, publishing messages, and waiting for message confirmations before closing the connection. Let's break down the code. Channel.confirm_delivery is called to enable publisher confirms. This ensures that the channel will receive acknowledgements, ACKs, and negative acknowledgements, NACKs, from RabbitMQ for each published message. Channel.add_on_ack_callback, handle_confirmations, and channel.add_on_neck_callback, handle_confirmations, register the handle_confirmations function as the callback to handle acknowledgements and negative acknowledgements, respectively. These callbacks will be triggered when acknowledgements or negative acknowledgements are received from RabbitMQ. The message_map dictionary is initialized to store the mapping between delivery tags and messages. It will be used to keep track of which messages have been published but not yet confirmed. If the message is successfully published, i.e., publish_result is true, the delivery tag is obtained from channel.next_publish_seek_no1. This ensures that the delivery tag corresponds to the message that was just published. The message and its delivery tag are added to the message_map dictionary to keep track of the message awaiting confirmation. If the message fails to be published, an appropriate message is printed. A list of messages is defined, and a loop is used to iterate over each message and publish it using the publish_message function. After all messages are published, a while loop is used to wait for all messages to be confirmed before closing the connection. The loop continues as long as there are entries in the message_map dictionary. Inside the loop, channel.connection.process_data_events is called to process any incoming events, including message confirmations. This allows the program to receive acknowledgements and negative acknowledgements from RabbitMQ and trigger the corresponding callback functions, handle_confirmations, to update the message_map accordingly. Once all messages are confirmed, i.e., the message_map is empty, the while loop exits. To start the message processing, the handle_streaming_confirms function is called at the end.